Welcome back, everyone, to today's Explainer. We're going to be looking at an absolutely massive breakthrough in artificial intelligence. Specifically, we're diving into a landmark paper from researchers at Google that literally shifted the entire landscape of how machines see and understand images. If you've ever found yourself wondering how AI image recognition got so good, so incredibly fast, well, you are definitely in the right place. We're going to unpack the exact architecture that made it happen step by step.
Okay, let's dive into this. At its core, this paper is essentially about creating a supergroup. Imagine taking two revolutionary AI architectures, two undisputed rock stars of computer vision, and mashing them up to see if they can play together. On one side, we've got the highly efficient Inception architecture. On the other, the deep training powerhouse known as Residual Connections. So what actually happens when they collide?
To find out, here's our roadmap for today. First, the image recognition revolution. 2. Streamlining with Inception-v4. 3. The residual connection mashup. 4. Solving the network crash. 5. Comparing the architectures. And finally 6. State-of-the-art results. Let's get right into it.
Starting with Part 1, the image recognition revolution and the rapid evolution of AI vision. To really understand why this mashup matters so much, we have to look at the breakneck pace of advancement right before this paper came out. The modern era of AI vision basically kicked off in 2012 when AlexNet completely dominated the ImageNet competition. Suddenly, deep convolutional networks were just everywhere. Object detection, video classification, the whole shebang. Following that, we saw rapid, incredibly fast milestones like network-in-network and VGGNet. Then, right around 2014, the Google team introduced GoogleNet, which we also know as Inception-v1. It was a total game changer for achieving great performance without needing a massive computational budget. But as the years rolled on, that Inception architecture kind of accumulated some technical baggage.
Which brings us to Part 2, streamlining with Inception-v4 and finally dropping that baggage.
Before the researchers could even think about combining architectures, the first of our rockstars needed to clean house. And this brilliantly illustrates the sheer scale of what they built once they actually did. What we have here is the pure Inception-v4 network. Historically, older Inception models were really constrained. They had to partition the model for distributed training using this older system called disbelief. It made the networks look way more complicated than they actually needed to be. But by migrating everything over to TensorFlow, all those memory constraints just vanished. The researchers were able to shed the unnecessary baggage and build a uniform, simplified, but incredibly deep architecture. Think of it like a highly efficient, multi-lane factory assembly line that handles massive complexity without ever getting tangled up in its own wires.
Section 3. The Residual Connection Mashup, or Building the Supergroup.
All right, so with a clean, streamlined Inception architecture ready to go, the researchers injected a huge concept introduced by Kai-Ming He and his team, residual connections. Now, what exactly is a residual connection? In really simple terms, it's the additive merging of signals that literally bypass layers in the network. Because Inception networks tend to be super deep, it's incredibly hard to push information all the way through them during training without the signal fading out entirely. Residual connections basically act like express lanes on a highway. They allow critical information to just skip the local traffic of certain layers and merge back in further down the road, which drastically speeds up the overall learning process.
Now, what's really interesting about this slide is just how elegantly simple this bypass mechanism is visually. You can see the signal traveling up, right? But then it splits. One path goes through the standard convolution layers, doing all the heavy lifting. The other path, that residual connection, arcs right around it and simply adds itself back into the output at the very end, right before the activation. It's a remarkably straightforward addition, but it's exactly what prevents the network from getting lost in its own depth.
So when our two rock stars finally form a band, this is what it looks like. This is the schema for the Inception-ResNet hybrid networks. The researchers basically replaced the filter concatenation stage of the traditional Inception architecture with these new residual connections. And they created two main versions. We've got Inception-ResNet v1, which matched the computational cost of the older Inception-v3, and Inception-ResNet v2, which was a costlier, much wider network meant to match the raw power of the new Inception-v4. The sheer scale of this hybrid network is honestly awe-inspiring, but forming a supergroup isn't always smooth sailing, is it? Moving on to Section 4, solving the network crash and the infamous 1,000 filter limit.
Yeah, so the mashup wasn't perfect right out of the gate. As they started scaling up, the researchers hit a massive wall.
They found that if the number of filters in the network exceeded 1,000, the residual variance started to exhibit some serious instabilities. The network would literally die early in the training phase. Seriously, after just a few tens of thousands of iterations, the last layer before the pooling stage would completely give up and start spitting out nothing but zeros. The AI was just crashing hard. The stakes were super high here, and standard troubleshooting was completely failing them. They tried drastically lowering the learning rate down to a microscopic 0.00001. No luck. The high learning rate phase would just destroy any progress anyway. They tried adding extra batch normalization to artificially stabilize the layers. That failed too. No matter what they did, the network just kept dying. So, what was the hero's fix? It ended up being a really simple mathematical tweak called activation scaling. They discovered that by simply scaling down the residuals by a factor between 0.1 and 0.3, specifically right before adding them to the previous layer's activation, the training stabilized perfectly. Even in smaller networks where this scaling wasn't strictly necessary, applying it never harmed the final accuracy, and it always helped stabilize the training. Honestly, it was a brilliant, elegant fix to a fatal flaw.
Section 5. Comparing the architectures. Did the mashup actually work?
Now that the networks were stable and fully trained, the big question remained: did adding residual connections to Inception actually make a difference? Let's move to the data and see how this builds across the different models on a standard image test. Take a look. You can see the older Inception-v4 sitting at a 5.6% top 5 error. Its residual counterpart, Inception-ResNet v1, is basically identical at 5.5%. But then we look at the heavier hitters. The pure Inception-v4 hits an impressive 5.0% error rate, and the hybrid, Inception-ResNet v2, it edges it out slightly at 4.9%.
So what does this data actually tell us? The core takeaway is right here. When you compare pure Inception to the Inception-ResNet hybrids, the final accuracy actually depends mainly on the sheer size of the model. The hybrid models didn't just magically create vastly superior accuracy compared to pure models of the exact same size. However, and this is a huge however, the residual connections offered a massive, indisputable advantage: training speed. The hybrid networks converged and learned significantly faster than the pure networks. They reached that peak accuracy in a fraction of the time.
Finally, Section 6. State-of-the-art results and the ultimate ensemble. If these individual models were this good on their own, what happens when they form an ultimate ensemble? Look at these results on the validation dataset. A previous state-of-the-art 6-model resonant ensemble hit a 3.6% top 5 error. An ensemble of 4 older Inception-v3 models also hit 3.6%. But look at that bottom row. The researchers combined one pure Inception-v4 model with 3 Inception-ResNet v2 models. They basically took the best of both worlds and pushed the boundaries even further, dropping the validation error down to an incredible 3.1%.
So, the crucial point is, when they took this ensemble and ran it on the official ILS-VRC test set to verify it wasn't just overfitting the validation data, they achieved a record-breaking top 5 error rate of just 3.08%. I mean, wow. At the time, this set an entirely new state-of-the-art for image classification. By dropping legacy constraints, streamlining the architecture, and injecting the raw speed of residual connections, they created an absolute powerhouse.
Which leaves us with a fascinating thought to end on today. The combination of Inception's efficiency and ResNet's depth training speed pushed error rates down to near 3%. It really begs the question, with models this deep, this fast, and remarkably accurate, what limitations in computer vision are truly left to conquer? Think about that as you process everything we've unpacked today. Thanks for joining me on this explainer, and I'll see you in the next one. Keep learning.